let's suppose you want the general solution to this differential equation. So you guess x of t equals e to the lambda t. You plug in the guess. And you find that it only works if this quadratic polynomial, a lambda squared plus b lambda plus c, vanishes for the lambda that you're looking at. So we saw all that last time, and we saw that this leads to a split into 3 cases. Let's say you end up in case 1. The case that I numbered 1 in the last video. Let's say you ended up in case 1, which was you got 2 distinct roots. Lambda 1 and lambda 2. Distinct means they are not equal. All right, then you have 2 solutions. Let's call them x1 of t and x2 of t. So x1 of t will be e to the lambda 1t, so e to the power some number times t. Sorry, this sentence is not finished yet. This is a definition. Then if we define x1 to be this and x2 to be this, these things are solutions to the differential equation, right? Meaning, x1 prime prime plus bx1 prime plus cx1 equals 0. Ax2 prime prime plus bx2 prime plus cx2 equals 0. We want the general solution. What do we do? So here's a fact about linear systems in general. Something that you learned about in Math 4a. Fact about homogeneous linear systems. If you find multiple solutions, then any linear combination of them is a solution. In other words, the way you probably phrased this in Math 4a, in linear algebra, is for a homogeneous linear system, the set of solutions is a vector space. It is a subspace of the collection of all possible functions that you could try. So let's see how to say this. The way you might have seen it, the notation you might have seen in a linear algebra class is if v1, vectors v1 and v2 satisfy the equation or are solutions to the homogeneous linear system, AV equals 0, then any linear combination, like C1 V1 plus C2 V2, is also a solution. And this is really easy to prove. You just apply the matrix A to C1 V1 plus C2 V2, and you use linearity. So this is the same word linear that's being used when we say that we're looking at a linear differential equation. So in the matrix vector setup, you just use linearity, meaning you distribute. You use the fact that it distributes like this. That's linearity. And then you're like, well, I assumed that V1 and V2 are solutions to the system. That means AV1 is 0 and AV2 is 0. So I get C1 times the 0 vector plus C2 times the 0 vector, which is the 0 vector, which is what I want to get on the right-hand side in order to convince myself that this linear combination here is a solution. Okay, so it's going to be the same deal when the vectors are replaced by functions and the matrix is replaced by a differential operator, like the operator that, when applied to x, produces what you see on the left-hand side here. So if we define L to be that stuff that's happening to x on the left-hand side, so an operator that takes a second time derivative, applies 2 time derivatives and then multiplies by a, and then adds that to the result of taking 1 time derivative and multiplying by b, and then adds that to c times, adds that to the result of multiplying by c. If L is that, then the differential equation we were looking at is L applied to x equals 0, right? This is just a way of writing ax prime prime plus bx prime plus cx equals 0. Is to just say L applied to x equals 0. And it's a linear differential equation in the sense that this L is linear. So that is something you can prove to yourself if you want to by applying L, using the definition of L, apply it to a linear combination of functions, and you will see that it distributes just like A distributes here. So that idea, that's linearity. If there's one thing you take from this course, I hope it would be this concept that linear differential equations are a lot like linear systems in linear algebra. So the analogy is just really, really strong. All right, so how does this help us? Well, we have 2 solutions, right? So we've got our x1 and x2. So when I say they're solutions, this one, e to the lambda 1t and e to the lambda 2t, when I say they're solutions, I mean when I apply L to them, I get 0, right? So we have L applied to x1 is 0, and L applied to x2 is 0, right? But L is linear. So L applied to any linear combination of these vectors, functions, any linear combination will be 0. For the same reason that it happened up here. L will just simply distribute over the linear combination, and then you'll get C1 Lx1 plus C2 Lx2. And since Lx1 and Lx2 are the 0 function, overall, when you take the linear combination of 2 zeros, you'll get 0. So that means this is a solution to the differential equation. So therefore, this function, let me call it x of t, c1 x1 of t plus c2 x2 of t, this is a solution to the differential equation. All right, and that is our general solution. Okay, now you might complain. You should complain a little bit. Why am I claiming it's the general solution? That's kind of jumping to a conclusion there. It's a solution. It's a family of solutions. Pick any number for C1 and any number for C2 and you'll get a solution. But does that give me a right to call it the general solution? If this is to be the general solution, then it needs to include all solutions to the differential equation. That's what general solution means, right? It means includes all possibilities. It's general. It includes all solutions to the differential equation. How do I know that I haven't missed any, that there aren't any other solutions? So it turns out that there is an existence and uniqueness theorem for differential equations of this type. And it goes very similarly to how the existence and uniqueness theorem for first-order differential equations that we previously discussed went. It says, given any initial value problem, there is a unique solution. given any initial value problem, there is a unique solution. There's exactly one solution to any initial value problem. An initial value problem in the case of a second-order differential equation, so if you want to make a solid prediction, will involve two initial conditions. So it'll be like the differential equation plus two initial conditions, maybe x of 0 and x prime of 0 or something like that. So let me write that down. So an initial value problem looks like this. You've got the differential equation, which is that, and then you've got two initial conditions. It doesn't have to be at time 0, but let's just say something like the value of x at time 0 and then the value of x prime at time 0. Something like that. So that is what an initial value problem looks like. And look at how many degrees of freedom there are for setting up an initial value problem. Once you fix the differential equation, each initial value problem corresponds to choosing two numbers, the initial value of x and the initial derivative of x. So there are these two independent parameters that you can specify in order to specify a particular initial value problem, a particular setup. The existence and uniqueness theorem says that to every one of these particular setups, there exists a unique solution. So there is a two-parameter family, or if you like, a two-dimensional space of possible initial value problems, and we have found a two-dimensional space of solutions. So there's a two-dimensional space of initial value problems, and we have found a two-dimensional space of solutions. Therefore, we have found all solutions. This is why this is the general solution. So let me make this even more solid of an argument. Since there are two free parameters, C1 and C2 there, okay, sorry, let me backtrack for a sec. So the argument is this: if we can solve any initial value problem, then we have found the general solution. If we can solve any if we can address any problem like this, no matter what x naught and v naught are, if we can find a solution, then since we know that there is a unique solution, there's only one solution to any setup like this, if we find a solution for every setup like this, then we will have found all the solutions, and so we will have the general solution. So that's the idea. Can we solve any initial value problem like this, regardless of the x naught and v naught chosen, regardless of the initial values? So I'm suggesting that yes, because there are two degrees of freedom in terms of what the initial values could be, and it looks like we have two knobs that we can control, two things that we can vary, C1 and C2. But is the answer really yes? Can we really solve any initial value problem, regardless of the x naught and v naught chosen? So in order to test, we need there to exist. So to solve, let's fix the initial values for a sec. For given x naught v naught, to satisfy the initial conditions, we need there to exist a choice of C1 and C2 here that makes the following happen. That makes the following true. So it needs to be that x of 0 is x naught. That means C1 x1 of 0 plus C2 x2 of 0 is x naught. And we also need x prime of 0 to equal v naught. So what I'm writing here is this equation. And then I'm going to write this equation. X prime of 0, well, that would be C1 x1 prime of t plus C2 x2 prime of t, and then plug in t equals 0. So C1 x1 prime of 0 plus C2 x2 prime of 0 equals v naught. So we'd need there to exist a choice of C1 and C2 that makes this system of equations true. Interesting. So we have found the general solution if this is possible. So in other words, we need a vector C1, C2 to exist that satisfies and now let me rewrite this setup here, but in matrix vector form. That satisfies this equation. We need a vector to C1, C2 to exist that satisfies this equation where the matrix of coefficients consists of these numbers. x1 of 0, x2 of 0, x1 prime of 0, x2 prime of 0. And we need this to work regardless of what the right-hand side is, right? So for given initial conditions x naught, v naught, in order to satisfy the initial conditions, we need there to exist C1 and C2 to make this true. But we need that to work regardless of the right-hand side. So need this to work regardless of what x naught, v naught are. Okay, this is something you've seen in linear algebra before. When does a linear system, matrix of coefficients on vector equals vector, when does a linear system have a solution regardless of what vector appears on the right-hand side? It happens when the rank of the matrix is full. So here there are two columns. So when the matrix has rank 2, that's when it happens. So I paused for a second there because I'm not sure that you actually heard that terminology necessarily, depending on what linear algebra class you took. Maybe you heard it described in terms of pivot columns or something like that. So if there were 2 pivot columns, then this would always have a solution. Another way of phrasing it, though, since this is a square matrix, the number of rows equals the number of columns, an equivalent condition would be when the columns are linearly independent. So when these vectors are linearly independent, or when the matrix is non-singular, that's when this has a solution regardless of what you put on the right-hand side. So linear algebra tells us that it does work. We need this to work. It does work if the columns are linearly independent vectors. So, why were we doing any of this? Because we're really concerned with whether we have actually found the general solution. Let me recap a bit. We want the general solution to this differential equation, right? So we made a guess, we plugged in our guess, and we got 2 different solutions. Then we decided, okay, then any linear combination of our two different solutions is a solution. And then we ask, can that help us with any initial value problem, regardless of what the initial values are? To answer that question, we wound up with this linear algebra setup. We said, yes, it can handle any initial value setup as long as the columns of this matrix are linearly independent. This is the same as, so it turns out the columns of this matrix being linearly independent is the same as saying the vectors x1 and x2, the functions x1 and x2 are linearly independent. So I'll say which works if x1 and x2 are linearly independent functions. So remember what I said earlier back here when I was saying there's like a two-dimensional space of possible initial value problems. And so we will have gotten all the solutions, we will have gotten the general solution, if we have found a two-dimensional space of solutions. Then that should cover them all. And then I argued, well, it looks like we have a two-dimensional space of solutions because I've got these two parameters, C1 and C2, that I can independently vary. Well, a linear combination of two vectors does not always guarantee that you're looking at a two-dimensional space. So if you imagine that the vectors, let's pretend the vectors are vectors in the plane, even though they're not, they're functions, so they're actually vectors in a very high-dimensional vector space. But just imagining for a moment that they're vectors in the plane, if the vectors point in independent directions, if they're linearly independent, then the collection of their linear combinations is everything. Their span is everything. So the general solution, which is like the span of some vectors, ends up being a two-dimensional solution space. However, if they line up, like if one vector is a scalar multiple of the other, or if they're otherwise not linearly independent, so that maybe you have three vectors and there's some other dependency, like they're sitting in the same plane or something like that, then, even though it looks like you have these two things you can independently control, you're still only manipulating a one-dimensional space of solutions. So, in this little doodle, the span of these two vectors would just be the line that they sit on, the line through the origin that they sit on. So what I'm trying to say is, if x1 is a scalar multiple of x2, for example, then the general solution that I'm writing down here is not really general. It would just be a one-dimensional space of solutions, which is not sufficient for solving any initial value problem here. And that's something you would see when you go to actually try to solve an initial value problem. You would run into this issue of the columns being linearly dependent. So there are some choices of initial values where there's no C1 and C2 that work. Okay, so this was all kind of a general discussion. It turns out, we reduced the question to everything works if x1 and x2 are linearly independent, right? It turns out that in case 1, where you have distinct lambda 1 and lambda 2, they are linearly independent. So these two functions are linearly independent. This video's kind of running longer than I wanted, so let me prove to you that they are in the next video, and I'll make the next video optional, and then so you can skip the next video and go to the video after that if you're already convinced that they're linearly independent. But for this video, just believe me that they are linearly independent. And so when lambda 1 is not equal to lambda 2, e to the lambda 1t and e to the lambda 2t are indeed linearly independent. So x of t equals c1 e to the lambda 1t plus c2 e to the lambda 2t is indeed the general solution. General meaning you can use it to satisfy any initial value problem. So any one of these setups here, you can use this. There exists C1 and C2 that will work for that setup.